So we're continuing to dip our toes in the AP waters, and we've been doing a lot of things with derivatives with Taylor polynomial approximations. Today's derivative type of problems aren't necessarily going to have anything to do with building with the magic formula, but let's just take a look. Here's some function f of x, and if you've been doing your memorizing, this is a very famous function f of x, but let's not worry about what it is right now, but it approximates a famous curvy function. If I wanted to know the derivative evaluated at 2t squared, how am I going to get that done? Now, by the way, there is no ninja involved here because what they're saying is you've already taken the derivative and now you're going to plug in a 2t squared. So don't look at this and think, well, there's something inside that has a derivative. Quite possibly if you were asked to take the derivative of this, yes, you might have a ninja. But in our case, we don't. So it's actually going to be pretty straightforward. If I'm going to plug a 2t squared into my derivative, then here's my original function, and I'm just going to write out its derivative. Now, some of you might see a clever way to do an optional eyeball adjustment to that, and it would look like that. But basically what I've done is I've gone term by term and taken the derivative of each one of these terms. It's power rule with a little bit of spiciness due to the factorial. Well, now that I have f prime of x, I need to plug in the 2t squared. So no matter which version you're using there, if I plug in the 2t squared, it looks like that. And at this point, I really have satisfied the request for f prime of 2t squared. It does look a little bit messy. Now let's see how we could have done this problem if we would have recognized f of x as a very famous function. Same problem, but now I recognize that f of x is really sine of x. I could still go term by term and get the same derivative I did before, but another thing I could have done is I could have said, all right, if I know f of x is representing sine of x, then I know that f prime of x is cosine of x, so I could have jumped straight to cosine of x if it's in my memory, and then I go ahead and I plug in the 2t squared. So f prime of 2t squared or cosine of 2t squared, I'm going to get the exact same answer as I did before. This might be more efficient for some of you. It might not be. So just know when you see something like this, in this case, there's really not a ninja in play. You're plugging in something into a derivative, calculate that derivative first, then go ahead and do the plug-in. Let's take a look how antiderivatives or integrals could show up in a situation like this. Okay, we're in a new scenario. I have a new f of x. This is not the previous f of x that we were working with. And also, if you have a good sense of memory, this is probably famous. But let's ignore that for right now. Here's f of x, and then they say h of x is going to be the integral from 0 to x of f of t, which is really f of x just with a t in there. And then after giving us this statement, they would ask, use the first two non-zero terms of h of x to estimate a value of h of 2. So that means we need to build h of x. But h of x is an integral of f of x. So this seems like it's pretty rough, but once you get used to this style problem, you'll notice that this is just fancy talk for h of x is the antiderivative of f of x. And later on, we're going to go and show you how I know that. But let's just assume right now that you're in the club and you realize that this language says h of x is simply the antiderivative of f of x. Then I can go through and just do the antiderivative term by term. So hold on here. So if I take this hint, then f of x can be rewritten, the antiderivative of f of x can be written as the equivalent of h of x. So I'm using capital F of x to represent the antiderivative of f of x, but term by term, antiderivative, 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 and antiderivative. This would be a good time to remind you, especially since these are pretty clunky, that if I want to check this antiderivative, let's say I want to check this term, I would multiply this out by power rule and see if I end up back there. And when I do that, I would have 3x to the second over 3 times 2 factorial. Those 3's would reduce, and I would have x squared over 2 factorial. That tells me that this was a good antiderivative of that. Same thing here and here. And also some other people might be looking at this saying, hey, 3 times 2 factorial is really 3 factorial. And you could write it like that if you want, but there's nothing wrong with leaving it this way as well. So now I have my h of x, and if f of x goes on forever, I probably should have done the dot, dot, dot. That means h of x is going to go on forever. And I'm just using this statement to say now I know h of x, so now I can do the first 2 terms to estimate the value of h of 2. So h of 2, notice the symbolism here. It's an estimate, it's not an equal to. And I plug in a 2, and I plug in a 2, so I get that, and you could just leave it like that because that's all arithmetic from there, and on an AP free response, it's okay to leave all the arithmetic. But if you're a fan of definitive answers, that works out to be a 2/3. So we know that the estimate of h of 2 is 2/3 because this was telling us we had an antiderivative situation. So let's go through and do the same problem, but show how I know that this is an antiderivative relationship. By the way, stick around to the end because I have a warning for you because this type of problem can be presented in a different way and then you're going to get a whole different answer. All right, so what we're doing right now is basically showing how did I know that that meant it was the h of x was the antiderivative of f of x. So this is what they told us h of x was, and because of your great calculus upbringing, anytime you see an integral, you consider the knee-jerk reaction of write the antiderivative and then install the limits of integration. Well, the antiderivative of f of t is capital F of t. My limits of integration go here. Now I'm going to plug in the x, and I'm going to subtract, plug in the 0. That's what that looks like. F of x minus f of 0. In this case, f of 0 ends up equaling 0. You could go ahead and check that out if you want. We will here shortly, which ends up equaling f of x. So this is showing that this, as I go through the mechanics of integration, leaves me with that, or it's the antiderivative of f of x, which is what we said on the other side. Let's do that same thing, but now let's do a little bit of nitty-gritty. Same thing, but now instead of doing the antiderivative in symbolism form, I go to that original function f of x, and I haven't done the antiderivative yet, but I'm soon going to do the antiderivative, but term by term. So f of x, which we're going to write as f of t, looks like that. When I do the antiderivative, it looks like that. Now I plug in the limits of integration, and it looks like a mess when I plug in the limits of integration, but it's not a mess because this whole thing's going to be 0. X goes into each one of these terms, then a 0 goes into each one of these terms, and I subtract them, but lucky for us, all of these are going to end up equaling 0. That's kind of the equivalent of this thing ended up being 0. And so we end up with just this, which is the antiderivative of f of x. So we showed it in 2 different ways, the actual mechanical way, the symbolism way, but in the end, most of the time, you're just going to say, hey, when I see a situation like this, I'm in an antiderivative situation. Now here's the warning I warned you about. This is pretty convenient when I put a lower limit of 0, but if my lower limit is not 0, we don't necessarily have this situation. So this nifty relationship would not hold if the bottom limit of integration was not 0. For example, if this situation said h of x equals this, Now I would have a different situation, and what I would end up having to do is I would go back to this, and where I see a 0, I would put a 1. That means I would put a 1 there, which means I would put a 1 there, which means I would have a 1 here, 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 and when I did this, this whole piece right here would equal a number. And I can still go through with all the calculations, but I'm going to end up with something slightly different than if I had a 0. So be careful, take a look. Is there a 0 there? If there's a 0 there and we're going to end up with a 0 phenomenon, we can jump straight to the antiderivative situation. But if there's not a 0 there, then I better go work out the math. If you're paranoid, always work out the math, and then you'll never be wrong.